Hello. We've been doing a lot of theory here in recent lectures for differential equations and linear algebra, and that does continue here in lecture 20A and 20B, but I want to start bringing us back into the realm of applications, and especially in 20A, we are going to look at free fall, not with linear air resistance as we did in the past, but this time with quadratic air resistance, and we will apply Euler's method to help us approximate solutions in that case. That will help us transition into some theory. Existence and uniqueness for nonlinear systems. We talked about existence and uniqueness for scalar differential equations before. And the implications for both autonomous and non-autonomous systems. You can see the content of lecture 20B. I'll talk about that when we get to lecture 20B. So again, coming back to applications, let's think about free fall. With quadratic air resistance, again, before we thought about linear air resistance, which is certainly the simplest model, but you might question whether it's as accurate as you might want. It all depends on the particular application. It depends on the particular object that you are trying to model. You always want to test the predictions against experiment, and I'll see if I can find some information about what kinds of models are best in what situations for lecture 21A. But let's go ahead and look at the math of a quadratic model. What if the magnitude of the force due to air resistance is not proportional to the velocity itself, but instead proportional to the square of the velocity? And I am talking magnitude here, so I'm not thinking about sign of the force, positive or negative here initially. I am thinking about up-down velocity with positive velocity when it's moving upward, negative velocity when it's moving downward. In other words, what if the absolute value of the force is some constant times the square root of the velocity? What kind of model would that give us? Well, it is a bit tricky, because the force itself does have a direction to it, and v squared is never negative. That means if we're going to have a downward pointing force due to air resistance when v is positive, and upward pointing force of air resistance when v is negative, we need to bring in the absolute value function in kind of a tricky way. We need to think of the force due to air resistance as negative k, where k is positive here, times the velocity times the absolute value of the velocity. Okay, pretty tricky, huh? Why does this work? Why is that a good idea? Well, when v is greater than or equal to 0, the absolute value of v is v itself. So you really would get a v squared there. You get negative k times v squared, which is what you see right here. On the other hand, when v is negative, then the absolute value of v is actually the opposite of v, which is a positive number. In other words, you would replace the absolute value of v by negative v, which again is a positive quantity if v itself is negative. But then when you simplify the algebraic expression here, the two negative signs would cancel, and you'd get plus kv squared when v is negative. Stop. Think about this. Does this make sense? Again, when the object is moving upward, when you throw it upward, v is positive, but the force due to air resistance is in the downward direction. It is opposing the velocity. The negative kv squared will give us a force due to air resistance that is negative, pointing downward. On the other hand, when v is negative, when the object is falling downwards, then the force due to air resistance is in the positive direction. It is again opposing the velocity. kv squared would be positive in that case. So this is pretty tricky, but this is the way to go. Therefore, when we combine this with the force due to gravity and use Newton's second law, F equals ma, we can say that m times the acceleration, which I can think of as the first derivative of the velocity, that's ma, equals the total force, which is the sum of these two forces, the force due to gravity, which always points downward no matter what, and the force due to air resistance. The force due to gravity is negative mg, negative sign meaning pointing downward, thinking of g as a positive quantity. And then we have the minus kv times the absolute value of v. We are adding these two forces, but because of the negative signs, we see two negative signs in here. Then we can divide both sides by m if we like, and write the equation this way. Negative mg divided by m is just a negative g, and then this thing divided by m gives you what you see right there. Okay? So that's our equation, a first order differential equation for the velocity as a function of time. We could try to solve this, And once we got a formula for v, we could try to integrate that formula really to find the height as a function of time. Perhaps that could be done, but it does look like kind of a pain, right? Because the absolute value sign in there, that's probably pretty unpleasant to deal with. I mean, doing integrals involving absolute value signs, oftentimes you have to break the integral into pieces, depending on whether, in this case, v is positive or negative. It sounds like it's perhaps doable, but not pleasant. Perhaps we should just use a numerical approximation like Euler's method. Maybe that would be less painful, well, especially with the help of technology. I mean, if we're going to do Euler's method completely by hand with even calculator help, it's kind of a pain still. But if we can program Mathematica with NestList to do this, that'll be nice. We can get the output pretty quickly. If we ultimately want to approximate y as a function of time, it is probably best, not absolutely necessary, to write this as a system and use the Euler's method for systems that I talked about in lecture 19a. Go ahead and let dv dt, v be dy dt to get a system. So this first equation is just the definitional relationship between the height and the velocity. Y is positive in the upward direction. So that means v is positive when the object moves upward and negative when the object moves downward. And dv dt is the same equation as before. This is a partially decoupled system. I could focus on solving for dv dt first in theory, again by separating variables. And then once I found that formula for v as a function of time, I could plug it back into this equation and just do a plain integration with respect to t to find y. But again, that sounds unpleasant because of the absolute value sign, so let's go ahead and use Euler's method. In vector form, this system would look like this. Boldface vector y is this vector right here. That's boldface vector y. First component, little y, the height. Second component, little v, the upward velocity. Though again, it can be negative because the object could be falling downward. And then, as a vector field, the formula for it is this. You kind of want to look at that and say it's like it's almost linear, but no, it's not. I mean, this is a nonlinearity. There's the absolute value sign in here. And in fact, you know, this does equal this, depending on the different values of v. It's definitely a nonlinear vector field. We cannot use matrices. Very soon we're going to be talking about how to use matrices to solve linear systems and something called eigenvalues and eigenvectors very soon, within the next couple lectures. So let's go ahead and apply Euler's method. Let's do 2 steps of Euler's method, quote unquote, by hand, well, with calculator help. You might want to have your calculator handy to do some checking of my calculations. I did check them, and so hopefully there's no mistakes. There still could be. Let's go ahead and pick some numbers. Let's take the mass to be 1, kilogram, k to be 0.1, and would have units that you could figure out based on the form of the force. That is different than I used for k for the linear model back a while ago, where k was 1. Here I'm using 0.1, so that might make the models not easy to compare, because the nature of the constant of proportionality technically is different. It has different units. But let's not worry about it too much. G is 9.8. Our initial condition vector, boldface y0, whose components are little y0, little v0, 0 and 20. Those are the same initial conditions I did use way back when. I don't remember exactly what lecture it was, maybe lecture 6 or 7 or so, when we talked about Euler's method for scalar equations, and we were looking at free fall with air resistance in that case. So this is a situation where, well, you're lying on the ground, and you got the ball in your hand, and you're throwing it up, straight up from rest with an initial velocity of 20 meters per second. Lying on the ground because y0 is 0. Oh, okay, well, you could take the ground to be y0 to be 0 when at the location where you let go of the ball if you want to. But then you'd have to keep in mind that it's not the ground in that case. Let's take delta t to be 0.01. That's the step size. We'll use Mathematica for more steps after the first 2 steps. So here goes. Here's the first 2 steps. You ready? All in one line. Did it all at once here. Here is our recursive equation for Euler's method in vector form. This is an autonomous differential equation. There were no right-hand side. On the right-hand side, there were no t's. So I can just write boldface f of y. It's the previous value of y, 0, 20, as a vector, plus delta t, the scalar, times this vector, the output of the vector field right here, f of 0, 20. That is a scalar times a vector. And I'm adding two vectors here ultimately. I'm showing this to you in vector form. Like I mentioned in the last lecture, in our textbook for my students, they focus on the components individually. You can do it either way. You can just focus on the y component and the v component individually, but you can put them together in a vector. Double check that this is what you would get when you plug the numbers in. I guess we should write down the formula for boldface f again if I can remember it. Its first component was v. Its second component was negative g minus, I think it was k over m, times v times the absolute value v. I believe that's correct. Maybe I should check. Yes, looks good. Okay, so there's our formula. So I'm plugging y equals 0, v equals 20 into that. Y equals 0. You don't see any y's in here. This thing is independent of y. Hey, that's kind of nice. It only depends on the v, actually. So I plug in the v there. That's the 20. And I plug it in here and here. 20 times the absolute value of 20, which, of course, is the same as 20 squared. Negative g minus k over m. K is 0.1. M is 1. That gives you 0.1 right there. Simplifies to this. Okay? Take the time to pause and double check that. Then let's do a second step. Although before we do the second step, we should ask maybe if this makes sense. We're throwing it up from ground level. Initial velocity of 20 meters per second. 0.01 seconds has gone by. You would expect the new height to be close to 0.2 meters. 20 times 0.01. And the velocity to be a little less than 20 because of gravity and because of air resistance, because of both effects, actually. 19.502 meters per second is our estimate for the velocity at time 0.01. Next step, same kind of general equation. y2 is the previous value, y plus delta t times the output of the vector field at y1. There's the previous value, there's your y1, right? 19.502, it matches this. 0.01 times the output of the vector field there, I'm plugging that point into f. And yeah, double check that all this is correct. And it looks like we get this. Notice the new value of y is not quite 0.4. It's the velocity is smaller. It shouldn't go up as much during the next 0.01 seconds. And the velocity, it's smaller. Okay. So we're going to use NestList and Mathematica as I've shown you. We could keep going with the steps. You know, usually when you apply Euler's method, you have an idea of how far you want to go. Where do you want to approximate the solution at? What value of t? But here, it would make sense to me to just keep going until y equals 0, at least approximately, because that's going to be approximately when the object hits the ground, according to the model. We'll also put the graph of the approximation from Euler's method in the phase plane and see how well it appears to be approximating the true solution. Just do a visual check to see if it seems reasonable, at least. Not that it's perfect, but does it seem like a reasonable approximation? So let's go ahead and use Mathematica now. Okay, I think we've got some time to go a little slower here with this lecture through the Mathematica. So I'm defining my right-hand side functions, little f and little g, that are going to go combine together to give me the capital F. I'm calling it g quad because it is a quadratic air resistance. Again, it's the magnitude of the force, its absolute value that's proportional to the square of the velocity. But when you look at the force itself, you need v times the absolute value of v in there. ABS does stand for absolute value. I am going to compare this with the linear mod, and I'm going to have a g linear in that case. The quad stands for quadratic. I can put these together with a list with curly braces here to give me essentially the vector field. I made the input here be a list with two elements here. Didn't actually have to do that. It ends up being nice doing a similar kind of thing when we use Euler's method and NestList to do that. So I'm sort of making a practice of doing that. And in fact, that's what I do right here. My EM function, quad, remember that's just the thing that I'm going to iterate with Euler's method. It's just my name for it. Okay, I could have called it something else, like just H or something. That would have been simpler. It's a three-dimensional kind of function, three-dimensional input, three-dimensional output. It's the iteration of this function that is going to do the do Euler's method, because to t I add delta t, 0.01. To y I add delta t, 0.01, times the vector field at that point. Its first component, this extra square brackets in there, is the first component of that. I am, in each component of this, thinking about needing to use the components of the vector field. I could have just done the little f there instead of the vector field first component. I could have just done that, but I chose to do it this way. And then for the third thing, it's the value of v, updating that, take the previous value of v, add delta t times the second component of the vector field. I could have just done the g quad there, but I put a 2 inside there. This syntax will do the second component. And then I iterate that function, I put it into NestList, and with a little experiment, I saw an experimentation, I found out that I need to do like about 260 iterations to get down to the y equals 0 approximately. So here's the output of this. And when you are at around 260 iterations, where'd it go? There we are, actually 259 iterations. That's where y, the first component here, is closest to 0. So this model is predicting that it will hit the ground after about 2.59 seconds. That's where y is closest to 0. And the downward velocity at that moment in time is predicted to be about -9. Well, the velocity is -8.9 meters per second, meaning it's going downward. That's the prediction. Is it reality? You'd have to test against reality. You'd have to do an experiment and see how well it does. Of course, there's lots of issues with the experiment, like what would k be? You'd have to do some other experiments to figure out k for the object ahead of time. And there's also just the question of whether the model is valid or not. Anyway, so that's the data output, but that's got the values of t. And if I want to graph this in the phase plane, I want to get rid of those values of t. Let me just do a semicolon here to suppress the output. Doing this will get rid of the values of t. Drop essentially is going to drop the first components of all those points to give me just values of y and v. List plot can plot that data. Here's a plot of it. I will look at a nicer plot that's got the axes labeled, but essentially this is the y-axis here, horizontal. This is the v-axis. We're starting out with an initial velocity of 20, initial position of 0. We're throwing it upwards from ground level, so to speak, or maybe shooting out of a cannon. These are the approximate points I get from Euler's method. I could connect the dots with a polygonal curve if I like. Just a bunch of straight line segments would be fine here to get the approximate curve. And you see what's happening over time is the velocity is going downward as it goes up because of the force of gravity and because of the force of air resistance. Y itself, the height, is going up because the velocity is positive. Once we get to there, the velocity is 0. That's where the object reaches its peak. At about 8 something meters would be the prediction. And then the velocity becomes negative. We're down below this axis, and y goes down towards 0. And again, it was about 2.59 seconds where it gets back down to 0. You don't see the t in here. You need to imagine it. This will show us the phase plane. I suppress the output here. I'm combining the phase plane with the solution curve. To get a visual feel for how well it's doing, I get to add the nullclines in there as well. This green line, that's the that would be the y nullcline because dy dt is horizontal here. Y is horizontal. Dy dt is 0 when a solution curve crosses that line. It's v equals 0. Dy dt equals v. That makes sense. And the brown line there is the v nullcline. Notice the vectors are horizontal there. That's where dv dt is 0, where there's no change in the velocity. That would be like a terminal velocity. We don't quite reach terminal velocity here, and in fact, in general, in these models, you don't actually reach terminal velocity. You only approach it. But we get fairly close to it here. It looks like the terminal velocity is predicted to be around perhaps negative 9.8. I'm not positive if that's the case, but that's what it looks like it might be here. If I changed k nav, it would affect the terminal velocity. And yeah, it seems like the solution curve is following the path of the vector field in the flow reasonably well. What's not so clear is whether this spacing between these points is truly accurate. You know, is this really a 1/100th of a second each time it goes? This is sort of stable enough in the sense that I'm imagining Euler's method is not doing too badly here. We could try a higher order method to get a better result, but it probably is not doing too badly. Okay? That's my guess. But again, that's a different question from whether it really models reality accurately or not. Again, you'd have to compare with experiment. Let's compare this with linear air resistance as well. So here I've got the linear vector field. I'm just going to go ahead and enter all this real quick. Essentially doing the same kind of thing except with the linear model. And it looks somewhat similar, but different. It's a little bit more, well, it's like more like concave up or concave down here, whereas the other one was initially concave up in the YV phase plane at least. Do notice that after the same amount of time, I think I did go the same amount of time here, 260 iterations, yeah, 260 still. Y is not back down to 0. So this is predicting, the linear model is predicting it's going to take longer to go back to ground level. It's also predicting a higher maximum height of around 18 instead of, I forgot the other one, what that one was. We can look at them together with grid. Look at these models at the same time. Yeah, the other one had a maximum height around 8. So it's a similar kind of pattern to the vector field in the flow, but subtle differences, numerical differences also as far as the prediction goes. Again, this one's predicting you hit the ground back at 2.59 seconds and have a maximum height around 8. This one's predicting you're not going to hit the ground yet for a little while, and the maximum height is around 18. Oops, wrong slide here. But wait a minute. Are we sure the solution even exists? And if it does exist, is it unique? These are important questions. If we were trying to approximate something that doesn't exist, that's kind of a bad thing to do. We're wasting our time. I mean, after all, the absolute value function that is a part of the formula for the vector field is not a super nice function. It fails to be differentiable at an input value of 0, right? Its graph looks like a V. It is continuous everywhere, but at the origin, it's got a corner in the graph, no well-defined tangent there. So h prime of 0 does not exist. On the other hand, our function in question here is V times the absolute value V. That is a bit nicer. Why? Well, let's think about its graph. H of V equals V times the absolute value of V. This equals V squared if V is greater than or equal to 0, and negative V squared if V is negative. It looks like a cubic, though it's not. It's two parabolas essentially pieced together. A parabola opening upward when V is positive, and a parabola opening downward when V is negative. This is continuous. It also turns out h prime of 0 exists. This is differentiable, and the derivative at 0 is 0. And in fact, h prime of V as a function of V is 2V if V is greater than or equal to 0, and negative 2V if V is less than 0. And that function looks like a V as well, a little steeper than the ordinary absolute value one. And that is continuous. So what I'm trying to say here is this h function, even though it involves the absolute value sign, is continuously differentiable everywhere. including at 0. It's differentiable, the derivative exists, and in fact that derivative is a continuous function. However, h double prime of 0 does not exist. Differentiate again, you're going to have a problem at the corner of the v. So it's still not super nice. It's a bit nicer, but still not super nice. But the continuously differentiable property will be enough to guarantee existence and uniqueness. Actually, the continuously differentiable property is necessary for uniqueness. Continuity is really all that's necessary for existence. It is enough. And not just because the initial condition for us was v equals 20. It would still be enough for existence and uniqueness even if v equals 0. That was the initial velocity if we were dropping the object from rest. It would still apply. We need to know the existence and uniqueness theorem for these general higher dimensional problems. Let boldface f of t comma y be a continuous, possibly time-dependent vector field. So I am allowing for it to be non-autonomous, for the t to be in there. Okay? Intuitively, that's a vector field that changes over time. This theorem does apply to that situation, although most of our examples will not be time-dependent. If we also suppose it's continuously differentiable everywhere and in all variables, which essentially means all the partial derivatives exist in our continuous everywhere. What kind of partial derivatives could we encounter? Well, in the simplest case, where boldface f of t boldface y, or vector f of t vector y, has components that are, well, two of them, it's two-dimensional, little f and little g. All the partial derivatives, partial derivative of f with respect to t, with respect to x, with respect to y, and the same kind of things for g with respect to t, with respect to x, and with respect to y. These all exist in our continuous everywhere. When I say everywhere, it's simplest to assume it's over the entire, all of, in this case, three-dimensional space, t, x, y space, although it could be valid over some domain that's smaller than all of that space. But let's go ahead and just assume these properties are holding everywhere. The conclusion, then, there exists a unique solution to the following initial value problem on possibly some very small time interval containing the initial time t0. Here's your initial value problem. dy dt equals vector f of t comma vector y, and y of t0 equals y0. Okay? Let's tease out what this means. And in lecture 21a, we'll go a little further in teasing out what it means, especially with regard to the flow property when it's autonomous, when there's no t on the right-hand side. But for this lecture, we're not going there. What does this mean? It means there exists a unique function, call it boldface, capital phi sub y0 of t, as we've done before, right? This is a solution function that satisfies the differential equation. The left-hand side and the right-hand side, when you plug it in, are equal over some interval centered at t0 here, from t0 minus epsilon to t0 plus epsilon, where epsilon could be a really tiny number. Phi prime of t, that is what you get when you plug that function into the left-hand side of the differential equation. F of t comma phi sub y0 of t is what you get when you plug it into the right-hand side. That's got to be true for all such t, in this interval, in other words. And the initial condition has to be satisfied as well. Usually t0 is taken to be 0, but here we're allowing for an arbitrary t0. Okay, so solutions exist. That makes us glad because that means we're not approximating something that's non-existent, right? The uniqueness has more important consequences in terms of interpreting the results. This is our last slide for lecture A. What are the consequences of uniqueness, both for autonomous and non-autonomous equations? And I'm going to illustrate these a bit with Mathematica, and then that will be the end of lecture A. For autonomous systems, not explaining this fully at the moment. It means the following. It means a solution curve cannot come back and touch itself, come back to where it started, unless it's a periodic solution. Now in lecture 19a we saw the van der Waals system, and we saw it had a periodic solution. That solution came back to where it started after a certain amount of time. That's not contradicting this, because it's periodic. It keeps going around and around and around forever and ever. But it can't come back and cross itself with two tangents that are not parallel for autonomous systems. No t on the right-hand side. Also, it means solution curves for two different initial value problems also cannot intersect unless they happen to sweep out the same overall geometric curve. The solution with this initial condition at time 0, say, might give you a curve that looks like this. You could have another initial value problem starting at another point at time 0, I don't know, call it z sub 0, along that same curve. It will follow the same curve. It will be the same curve. That's the conclusion here. Because they can't intersect unless they happen to sweep out the same geometric curve. They solve different initial value problems. You're starting at different spots at time 0, but as time goes on, they sweep out the same curve, both as t goes increases and as t decreases, actually. In the plane, you can say even more. Two-dimensional systems. Like with the van der Waals equation, you can say that if there is a periodic solution, then solutions with initial conditions inside the periodic solution must stay inside that periodic solution for all time. Like we saw with van der Waals, we had a periodic solution that looks something like this. Goes around and around. If you've got some initial condition inside there, the solution curve with that initial condition has to stay inside the periodic solution. There's no way it can get outside of it, because if it did, it would touch it. And that can't happen with autonomous equations. Again, I'm not explaining this fully. I hope it makes some intuitive sense. I mean, if the vector field, with an autonomous system, the vector field is static, it doesn't change over time. Hopefully that makes some intuitive sense that it couldn't possibly go across that other solution, that periodic solution. In spite of uniqueness, these three properties do not necessarily hold for non-autonomous systems. You might scratch your head and wonder why. You know, what's the difference between autonomous and non-autonomous? Uniqueness still is true. That theorem on the previous slide still involved t on the right-hand side in general. But you can't conclude these things. Intuitively, this is because the vector field for a non-autonomous system is changing over time. I'll show you Mathematica here in a second. As an example, we can consider something called the forced van der Waals equation in the system. Here it is as a second-order scalar equation. Notice I put a forcing function on the right-hand side here, a cosine omega t, where a and omega are constants, is some sort of external forcing. You know, if this is an electric circuit, there's some sort of external forcing going on with the current, for example. As a system, we could write it like that. Let's go ahead and look at this in Mathematica. That'll be the end of lecture A. So this is the forced van der Waals system here. Notice the G depends on t. It involves an a cosine omega t like you see here, and also the vector field is time dependent. The direction field changes over time. The vector field changes over time. It's not static. This is some code that will allow us to animate the direction field in this case. As time goes by, for example, I've got nullclines in here, but realize, at least with the brown nullcline, that changes over time as well. And I'm not sure why it's making the vectors different lengths here. I thought I made them the same length when I did this on my computer. Let me add an option in here. Vector scale, 0.03, 0.039, I think will work. Okay, now, well, okay. I don't want line segments, I really want vectors in a vector field here. Let me make this one 1 here. There we go, that's better. As time goes by, the nullclines change, the vectors change. Solutions still need to follow the vector field, but the vector field's changing. How does that happen? They can still follow it. At any moment in time, if a solution curve is at the tail of one of the vectors in the vector field at that moment in time, that vector in the vector field will be a velocity vector for the solution curve at that moment in time. I'm using Euler's method here, and we're going to see a solution curve, well, an approximation to a solution curve with Euler's method. Following the vector field, notice it just crossed that brown nullcline with a horizontal tangent, but the brown nullcline has moved a little bit further, and now you see it's no longer a horizontal tangent there. Right there, it's crossing with a horizontal tangent. But because the brown line, that nullcline is moving, it's no longer a horizontal tangent there. It's no longer even crossing it. And we can keep letting this go. And notice what happens here. Some kind of strange looking behavior is happening with the approximation. We are seeing something that kind of looks like the periodic solution, but we're seeing extra dots over here and in here. And in fact, if you watch this carefully, the solution curve does cross itself. And that shouldn't be surprising because it's not autonomous. Okay? So we'll look at more examples in lectures to come. Thanks for watching.